Welcome to Coherent Solutions Test System Configurations for 100 gig and 400 gig transceivers. I'm your host, David McCormick, Technical Sales Manager for North America. In this presentation, we'll be talking a lot about the optical transceivers used for datacom and optical links. We'll be focusing primarily on the 100 gig and 400 gig varieties. You'll see a lot of acronyms such as QSFP, SFP, CFP, and whatnot. If you care to know any detailed information about any one particular transceiver, I encourage you to go online to Wikipedia, the IEEE standards, or the particular multi-source agreement for any given transceiver. Coherent Solutions is one of the only vendors for optical test and measurement in the PXI platform. Many of the icons and instruments you will see in these test diagrams are all available from Coherent Solutions in the PXI form factor. The variety of PXI modules include tunable lasers, optical power meters, optical spectrum analyzers, variable optical attenuators, ODE converters, optical switches, and many passive component integrations. There's many other instruments that are not shown on here. For a complete list, go to www.coherentsolutions.com, and all datasheets and instruments are online. As a reminder, any instrument that Coherent Solutions provides in the PXI format is also available in standalone benchtop formats known as the Matrix series. Anything you see in PXI is also available as a standalone controlled over USB or Ethernet in a small benchtop form factor. Okay, so let's get into our first system diagram slide. It's a little busy. I'm going to spend a lot more time on this first slide to explain what each of these things mean and how to use the various pieces of information on these slides to your advantage. We'll speed up as we go through, so bear with me. The first thing to note on these is there's a nice big box in the upper section here. This contains some of the pertinent information for each of the various transceiver application codes. By application codes, I mean these terms here. The IEEE has terms such as 100G base-SR10, 100G base-SR4, and so on. Each of these application codes stands for a different type of transceiver. Included in this is some handy information. You'll see in this form factor column here, it describes the kinds of modules that particular IEEE standard is supported in. For instance, there are CXP, CFP, QSFP28, QSFP, and even SFPs. In this next column, I give you a handy indication of how many independent data channels there really are for that particular transmitter. For instance, on this page, what is highlighted is the 100G SR10 transceiver. This particular transceiver has 10 independent data lanes, each one running at a data rate of 10 gigabits. That gives you a total of 10 times 10 gigabits or 100 gigabits. In addition, I indicate what kind of modulation format you can expect for this transceiver. In this case, this is a 10 gig NRZ, which stands for non-return to zero, essentially ones and zeros, as opposed to multi-level signaling. Transceivers can also use a variety of wavelengths. In this column, the particular transceiver that we're looking at here uses 850 nanometers. Others you will see have a combination, especially for wavelength division multiplexing. Underneath the connector column, you can see what kind of physical connector is used on the front of these optical transceivers that have both optical transmit output and optical receive input. MPO24 is a connector standard that has up to 24 optical connectors. Other more traditional are dual LC connectors, so you can use this as a handy indication as to what kind of optical interface there is on that particular transceiver. In addition to the data rates and the formats and the optical connectors, there's also a variety of fiber. The two main ones are either single mode, which is indicated by this OM3, or SM, indicated by SM here. In the last column, there is a typical distance that these transceivers support for transmitting. So in the case of this first test receiver, we have a 100-meter capability that has 10 separate transmit, 10 separate receive lanes, each running at 10 gigabit. Like I said, I'll spend more time in this first slide so you understand what each of these little icons in this test system are, and then we'll be speeding up. We'll start with the DUT style here. We're talking about the 100G SR10 transceivers here, which can be in a CXP, CFP, CFP2 or 4, or a CPAC format. As you can see here, they have 10 separate lanes of information running at 10 gigabits. You'll find the DUT down here on a test fixture. The test fixtures will vary from test setup to test setup because the form factor for the DUT literally changes. In this case, the test fixture has to support at least 10 differential transmit signals and also 10 differential receive signals. So let's start with the transmit signals themselves. In order to drive the test fixture transmitters, we need a pattern generator, and that's what is denoted here by these PPG birds. PPG stands for pulse pattern generator, and BERT stands for bit error rate tester. Since we have a total of 10 transmit signals, we need a total of 10 independent transmit signals from these PPG birds. This particular transceiver is running at 10 gigabits. Therefore, we need to have a pulse pattern generator and a bit error rate tester that can run at least 10. 14 gigabit is indicating what these boxes are capable of here. In order to have a total of 10, we take 4 from one box, 4 from another PPG box, and then 2 from the last one. This gives us a total of 10 transmit signals. Let's now walk through the diagram starting at the transmit end of the transceiver. Here we see that there's a single cable known as an MPO24 style. This kind of cable can literally carry 24 signals. Again, the connector style is indicated up here at the top in this handy box. All the transmit and receives are being carried on this single cable. But in order for us to get to the test signals, we need to really break this out. So we're going to run this MPO24 into an MPO breakout. This is really nothing more than an MPO connector on one side and up to 20 individual connectors on the other. By breaking out these individual connectors, we now have access to each of the 10 data lanes that are available on the transmit side and also the 10 data lanes that are available on the receive side. Once we break out these 10 individual transmit signals, we run them into an optical switch. The optical switch allows us to select one of any of the 10, transmit 1 through 10, and pass it on down to the next instrument. Once we have isolated one of the 10 transmit signals that we want to analyze, we can run it through another optical switch. In this case, we have a choice of many different test fibers that we could run the signal to. These might emulate the maximum distance, which is indicated up here, 100 meters. For instance, this may be 120 meters of fiber to add a little bit of margin testing for the dispersion of the transmitter. With the extra ports in the optical switch, you can test other things. In this case, we show an optical spectrum analyzer. This is a device, of course, that looks at the wavelength. In this particular case, we only have one particular wavelength, and that is 850 nanometers, as you can see at the top of this box here. So it doesn't really add a lot of value. But in the case where you have multiple wavelengths, you may actually want to measure the optical spectrum of the transceiver before you go any further. Once we go through these optical test fibers, or optionally the optical spectrum analyzer, we again have another optical switch here. This allows us then to redirect the signal either down this path or down this path. When we choose the optical switch such that the path is going in this direction, this redirects the transmit signal back through a variable optical attenuator that has an inline power meter. This allows us to change the optical power level on the signal and reduce it to test the sensitivity of the receiver. We can pass this into an optical switch, and that way we can redirect any one of the transmit signals to any one of the 10 receive lanes. Once we have directed the signal to receive lanes, these receive lanes are very similar, and we've jumped to the next standard here, SR4. You'll see that this is very similar to the previous slide, but instead of having 10 separate lanes at 10 gigabits, we have 4 separate lanes running at 25 gigabit for the same total of 100 gigabits. You'll see that the test system is very similar. So let's continue that path. We were sending a transmit signal back down here through our VOA inline power meter, and then again into an optical switch, which allows us to send this back through our MPO breakout cable. This then goes back into the transmitter, transceiver, known as a transceiver. In this case, we can stimulate any one of these 4 receive signals, which is then being routed back to the bit error rate tester here. The purpose of the bit error rate tester is, of course, to measure the error rate. Normally, when there is no attenuation and the transmit signal only has a few dB, you will have error-free operation, as indicated by the error rate that this bit error rate tester is measuring. However, remember, we have a VOA in series with this optical path that is returning the transmit signal to the receive side. By increasing the optical attenuation, we can keep attenuating the signal until such time the bit error rate starts noticing when errors occur. This allows you to determine the sensitivity of that particular receive path. By selecting one at a time each of these receive paths, you can stimulate each of the receives. Again, you can transmit any one of these transmits and to the other receiver. Traditionally, the transmit for channel number 1 will be used to stimulate receive channel number 1, and so on. Transmit channel number 2 will use to be stimulating receive number 2. Okay, so that's the bit error rate path for sensitivity on this particular slide. Now let's look at the other path that goes to the oscilloscope. In this case, we use the optical switch to route the optical signal down this way. We come down to this 10-90 splitter, which indicates a 10% split in one path and a 90% split in the other path. Let me explain why we need this splitter here and why you may be able to get rid of it in your particular test system. Equivalent time scopes, which is what I'm showing here, require a trigger in order to look at the optical waveform. This is as opposed to a real-time oscilloscope, such as from Tektronix or Keysight Industries or LaCroix. In the case of an equivalent time sampling scope, such as a Tektronix CSA 8300, the scope does require a trigger. Now, many users may ask, why not use the trigger from the clock of the original transmit signal, which is over here? And in some cases, that is fine. However, once you start transmitting signals through longer lengths of fiber, you will notice that the inherent drift in the trigger signal relative to the actual waveform you want to measure becomes unacceptable. In order to work around this problem, what is happening is a portion of the signal is going through a high gain ODE converter. This is not a very good analog converter, but rather a digital optical to electrical converter. It then drives a clock recovery circuit. This is very similar to the clock recovery circuits that you have in most transceivers these days. This clock recovery circuit actually generates a clock which times in the data. A divided down version of this can be used for triggering the oscilloscope. By recovering the clock in this manner, you will generate a very clean low jitter signal in order to have the best results for analyzing your non-return to zero pattern here. However, since we want the best signal to noise ratio possible, we actually have the 90% side of the splitter splitting off here. In certain cases, this 90-10 split could be a 95-5% split, or even in some cases a 99-1% split. The idea here is you want the majority of the signal to be going to your analog ODE converter. The analog OD converter has various requirements depending on the standards, but in general it's called a reference receiver. The reference receiver is a definition of the bandwidth of a particular receiver for a particular standard. In this case, we see that we're working with a 100 gig SR4, and each of the signals is running at 25 gig NRZ. Traditionally, non-return to zero signals require an ODE converter and an oscilloscope combination, which have approximately 0.75 times the clock rate. So in this case, it would be 0.75 times approximately 26 gigahertz. Sometimes this is implemented in hardware, sometimes this can be implemented in the actual DSP software inside the oscilloscope. It depends on whether or not you have frame trigger capability or whether or not you want to go with hardware filtering on these ODE converters. In modern oscilloscopes, this filtering can be done all in digital signal processing if you have the right frame trigger and you actually know what pattern you are generating here. I'll talk more about that later. It's not required for non-return to zero signals. It is required for PAM4. We'll get to that later when we get down to our PAM4 signals, which are shown in some of these other standards, especially for 400 gig. So in review, what are we actually able to measure with this system? The ODE converter has an optical power meter built in, and so we can actually measure parameters such as the eye pattern. We can look at the margins on the testing. We can look at the jitter on the signal. When we're looking at the bit error rate, remember we have an optical attenuator in series, and so we can do some basic sensitivity measurements of bit error rate versus optical attenuation, which ultimately is bit error rate as a function of the optical power that is coming back into the receiver. Optionally, of course, we can look at the actual optical wavelength. These are the basic measurements that test most of the capability of an optical transceiver. This test system does not have some of the more exotic measurements such as dispersion penalty and other things which would require more equipment. But you'll find by measuring the bit error rate as a function of power level as well as the eye pattern, you can pretty much guarantee 99% of the time the functionality and the in-spec performance of an optical transceiver. And as I mentioned before, I'll be moving faster through these slides. As you can see on this particular standard, this is known as a 100 gig SR2 BIDI, or also known as bidirectional. The reason is because instead of a single wavelength, we actually have two wavelengths, as is indicated by this here. So although there is only one transmit fiber and one receive fiber, this is actually carrying two separate wavelengths. Because of that, further down through our network, we actually need to use a device called an optical demux. This optical demux here is designed for splitting out the 850 nanometers from the 910 nanometers. Then by using the optical switch, we can sequentially test either the 850 nanometer or the 910. This is the basic functionality you will see repeated. The optical demux does need to be optimized for the particular standard. As you can see, there are other standards that use wavelengths such as the 1296, 1300 nanometers, 1305, and 1308. There's also some standalone rates that run at the O band in the 1300 nanometer. Just be aware that since we're working with a multi-mode standard, and two, that this optical mux is really optimized for multi-mode fiber and these two wavelengths only. This is a component that would need to change depending on the wavelengths for these other standards. Now let's take a look at one of the single mode standards. This is an interesting standard. If we look at this is called a 100 gig DR. It's in a SFP 112. SFP stands for small form factor pluggable. Traditionally, these have only been 10 gigabit parts, but there are standards now where a single channel with a single 1311 nanometer wavelength is running at 100 gig. In order to accomplish this, it's running at a 50 gigabaud, which is a 50 gig clock rate, but it's actually transmitting a PAM4 signal. PAM4 signals are 4-level signals, as you can see on the oscilloscope here. 4 levels corresponds to 2 bits. So for every baud clock rate unit interval, a PAM4 signal is transmitting the equivalent of 2 bits. At 50 gigabaud, 2 bits equals 100 gigabit total. So in this case, we actually have a single mode DUT, as you can see here. Because this DUT is single mode, the instruments that are used in this test diagram are compatible with single mode fiber. As opposed to the previous slides, we were working with multi-mode fiber. In this case, we have a single mode fiber that comes into a splitter. Let's see what happens when we go up to the 90% path versus the 10% path. Let's talk about the 10% path first. The reason that this signal is here is that a small portion goes out and through an optical attenuator to a very high reflection termination. Essentially, this is a mirror. So whatever signal we send down this way will come back through the attenuator, and it will experience again the attenuation which is set here. For instance, if this VOA is set for 5 dB of attenuation, the signal will have 5 dB of attenuation going through in this direction, and once it reflects back, it will have another 5 dB of attenuation coming back. So ultimately, we'll have at least 20 dB of attenuation, 5 from a double pass to the VOA and another 10 dB approximate because of this small percentage here. The purpose of this signal is to intentionally introduce what is emulating a bad reflection in the network. So although this may be at a power level that is about 20 to 30 times below, reflections can get back into the laser and cause problems. Various standards may have a defined amount of reflection that you must apply while you're doing bit error rate testing or eye pattern testing. There are more than one way in order to accomplish this. With single mode fiber, this could be done with a circulator, but what I have shown here is a very simple double pass attenuator and reflector. Now let's look at the 90% path. Most of the signal is going through, and here we see a very similar structure that we saw on the previous diagrams. We can go through a number of test fibers, but in this case, remember we're working at a standard here, which has a 500 meter distance. That's why these test fibers would change depending on the transceiver that you were testing. In this case, this may be a 600 meter length of fiber. Again, the optical spectrometers would be optional. We again use another series of optical switch banks in order to either direct the signal back to the receive side of the transceiver for bit error rate testing, or we can send it down this path to again go through the clock recovery circuitry, a linear ODE converter that has the proper bandwidth for this data rate, and again into the oscilloscope for analysis. Please note, and in this case, we were actually working with a standard known as PAM4. As we mentioned earlier, that means there's 4 distinct levels in the optical signal. The requirements for the ODE converter and the filtering are slightly different than the traditional NRZ. I won't go into too much depth, but let me just say that most of the filtering in the modern oscilloscopes today is handled through digital signal processing. Again, on an equivalent time scope, such as a Tektronix CSA 8300, in order to accomplish this filtering, you must be triggering the scope with a known pattern and have a recovered clock or the original clock with low jitter from the pattern generator. Please note that although this SFP112 and this 100DR seems like a very simple solution, you have a single mode fiber with a single wavelength running at 100 gigabit, it means that the test equipment has to run at a higher speed. This means that this pattern generator has to actually run not only at 56 gigabaud, but also capable of generating the PAM4 signals as we're going to be analyzing on the scope. Because of that, this equipment may be a different piece of equipment, or definitely much more expensive than the preceding slides where we had 10 gigabit. Keep in mind that you may need to change these bit error rate test and pattern generators out, determined by the data rate of a particular transceiver you're trying to test. So now that you've seen the basic functionality in a few of these slides, let's go a little bit faster and look at this. Here you can see that we have multiple application codes circled up in the box. This means that this particular test system that I'm showing can actually test all three of these application codes. That's because they have some similarity. As you can see here, these are all using 4 wavelengths here. They're slightly different between these standards. So the test system is very similar, except down here where we have optical demuxes, I have 2 different styles here. One for the CWDM4 of this standard and one for the ER4 LR4 standard here. This is really the only difference in this test system. This happens to be running at 25 gigabits for every data lane, so there are 4 data lanes running at 25 gigabit. In this case, we are using NRZ or non-return to zero, so we do not require a bit error rate pattern generator that has PAM4. This simply needs to run at 25 gig NRZ. Keep in mind that since this is a coarse wavelength division multiplexing style, it may be very valuable for you to look at the actual wavelength on each of the individual 4 transmit signals. In this case, the optical spectrum analyzer that was somewhat optional on the previous slides is something you probably want to include here in this test system. In our very first setup, we saw 10 parallel signals with multimode fiber, each carrying 10 gigabit. In this case, what we're looking at here is known as a PSM4. This means that there's literally 4 parallel transmit signals, each one running at 25 gigabit. Because they have their own fibers, it does not need to be multiplexed. It simply have a single laser that's anywhere within specifications, in this case 1300 nanometer. So this is very similar, except now instead of parallel multimode signals, we have parallel single mode signals, but then it requires a similar kind of breakout, again similar kinds of optical switches, and ultimately going to be tested by the oscilloscope for the NRZ pattern. Now, as you see, we've moved on to 400 gig standards. The 400 gig standards are in many respects very similar to the 100 gig, but of course they're ultimately running at a total data rate that is 4 times higher. Because of that, you'll see a lot more parallelism and also a lot more PAM4 type signals. I'll just quickly go through this so you understand. We have a different form factor here known as the QSFP DD, which stands for double density. There's also an OSFP, which stands for octal small form pluggable. So again, the test fixture needs to accommodate the actual data rate. The bit error rate transmitter also needs to accommodate this higher clock rate. In general, multimode 400 gig transceivers require a 56 gigabaud capable pattern generator with PAM4 levels. At this point, we've explained enough of the systems that I think you can follow what's happening here. So in this case, we have 4 parallel signals, each one carrying 100 gigabit worth of information. All the components are very similar and can in fact be reused if the fiber type is compatible. Again, remember the fiber type is listed up here. You can see that this is multimode OM4, and as such, these multimode switches that you see here are the same multimode switches that we used in the previous slides. The main difference between these faster 400 gig signals and the 100 gig is most of them used of the PAM4 kind of protocol here. Again, remember the PAM4 is 4 different levels, which carries 2 bits. So for each clock symbol, we are carrying 2 bits times the clock rate that is available. So in this case, since we are running at 56 gigabaud with 2 bits, each one is carrying 100 gig, and there are 4 lanes. 4 times 100 gives us the 400. Another big difference between the 400 gig rates and the 100 gig rates is the way that the oscilloscope testing is being done, namely the filtering for the ODE converter. Previously, for NRZ signals and old legacy 10 gig signals, the filtering tended to be performed by actual hardware filters. Since we actually have frame triggers that can be available due to the clock recovery, we can actually recover the entire waveform. Once we can recover the entire waveform, since we know the pattern, we're able to perform digital signal processing on it. Digital signal processing allows us to implement any kind of filter that we want on the incoming signal. The important thing to note here is that in the actual transceivers that are being used in 400 gig circuits, there are many feed-forward equalizers known as SFE 5-tap. What these do is these recover the signals that would look really rather ugly if you did not add this equalizer after the fact. The intent is that the oscilloscope can basically emulate the FFE 5-tap filter inside using software and digital signal processing rather than actually having hardware filters inside. Because of this, it can quickly adapt between many different standards. So, what is required is an oscilloscope, whether it be equivalent time or real time, that has this filtering capability built in order to actually measure these PAM4 signals. You'll also notice a term here as TDEC analysis. TDEC-Q is a new standard of testing that is slightly different from our traditional eye pattern. The important things to know is that you have to have these software filters for 5-tap built into the oscilloscope, as well as the capability to analyze PAM4 signals. One of the changes introduced with this new TDEC-Q analysis is that instead of a PRBS pattern coming out of the pattern generator, there is a new pattern known as the SSPRQ, which stands for Short Stress Pattern Random Quaternary. In layman's term, this pattern contains really all the worst case scenarios for short-term and long-term jitter and data-dependent patterns. It's a 2 to the 16th pattern that really contains the worst case flat spots and repeating patterns, both 1010 as well as long flat spots. Please keep in mind that this SSPRQ pattern is not available in many of the old pattern generators and BERT generators. To do PAM4 testing to be compliant, you require this virtual FFE 5-tap filter on the oscilloscope side, and you also require the pattern generator to adhere to this SSPRQ type pattern. Here you see another bidirectional, but for 400 gig. In this case, you can actually see that we have a 50 gig baud rate here, but we're running at PAM4, and we also have 2 wavelengths. Again, from the narration we did on the previous slides, you can figure out what's going on here. One thing worth mentioning on these rates, when we move to TDEC-Q analysis here with the required SSPRQ pattern, the requirements for the OD converter have actually been relaxed quite a bit. Traditionally, for non-return to zero, the OD converter needed to be approximately 0.75 times the data rate. In these new PAM4 kinds of configurations, the OD converter is actually almost half of the data rate. That would seem amazing, but remember, this virtual 5-tap FFE here actually recovers a lot of the signal. So in order to make it easier for the test and measurement to have higher bandwidth OD converters, they actually reduce the requirement to be half of the baud rate. So in this case, we only require an OD converter that has nominally 13.28 gigahertz worth of bandwidth. So even though we're running at a higher data rate, in some cases the OD converter may actually have a lower bandwidth requirement depending on the standard. The 400 gig uses a similar variety of methods in order to carry the data. In this case, we actually have a single wavelength, but we're carrying on a parallel fiber. So we actually have 4 separate fibers for the transmit, and there's also 4 separate fibers for the receive. Each of those fibers is carrying a 100 gig signal, running at 56 gigabaud with the PAM4. Again, I think you can figure out what each of these pieces is doing from the previous explanations on the other slides. Okay, let's move on to the Again, in this standard, we see the use of CWDM4, which actually has 4 separate wavelengths, and that's why the optical spectrum analyzer is very important. This is very similar to the CWDM in the 100 gig, except of course everything is running with a PAM4 signal at a higher data rate in order to accomplish the net goal of getting to 400 gig. And as we're approaching the end here, you can see that some of these systems are quite flexible and are able to measure multiple standards. In this case, this test setup is able to measure 400 gig FR8, 400 gig LR8, and 400 gig ER8. Primarily, these standards differ by the specification of how far they can actually travel down the fiber. As you will see, they go from 2 kilometers, then to 10 kilometers, all the way up to 40 kilometers here. Physically, they're very similar, except they just have different tolerance for how long they can go down the fibers. Of course, the test fibers here may need to be very different between these different standards here. Otherwise, as you can see, the components that are used in the system are really very similar to some of the other components at the lower data rates. Okay, so we've reached the end of the presentation, and thank you. Feel free to contact me if you have any questions about the diagrams in this presentation.